There's something unsettling yet utterly fascinating about the universe when it refuses to follow the rules. Picture this: a black hole, nature's ultimate cosmic vacuum, designed to devour everything in its path, suddenly stops. It defies gravity's relentless pull, resisting collapse in ways that leave even the brightest astrophysicists scratching their heads. These aren't just theoretical quirks, they're real, observed anomalies that rip holes in our understanding of space and time. What if everything we thought we knew about black holes, those inescapable pits of darkness, was just the tip of the iceberg? Today, we're diving into one of the universe's most perplexing mysteries: black holes that didn't collapse as expected. These cosmic rebels challenge the very foundations of physics, whispering secrets that could rewrite the rules of reality. From the supermassive beast at the heart of galaxy M87, spinning defiantly against its own demise, to primordial relics lurking in the shadows of deep space, each anomaly is a breadcrumb leading us toward something profound. Could dark matter be propping them up? Are quantum forces stitching their edges together? Or is there something even stranger at play, something we haven't dared to imagine yet? This isn't just a story about distant cosmic oddities. It's about the human quest to unravel the universe's greatest puzzles. Every stubborn black hole is a clue, a challenge flung across the cosmos, daring us to think bigger. As we journey through mind-bending theories, gravitational surprises, and the tantalizing hints of hidden physics, remember, you're not just watching a video. You're stepping into an ongoing detective story, one where the stakes are nothing less than the nature of reality itself. So buckle up. By the end, you'll never look at the night sky the same way again. Black holes are born from the dramatic deaths of massive stars, cosmic giants at least 20 times heavier than our Sun. These stars spend their lives burning through nuclear fuel, fusing lighter elements into heavier ones in a desperate battle against gravity's relentless pull. But when the fuel runs out, the battle is lost. In a matter of seconds, the star's core collapses under its own weight, triggering a violent supernova explosion that blasts the outer layers into space. What's left behind is a core so dense, so unimaginably compact, that not even light can escape its grip, a black hole. At the heart of every black hole lies a singularity, a point where matter is crushed to infinite density, and the laws of physics as we know them break down completely. Surrounding it is the event horizon, the infamous point of no return. Once anything crosses this boundary, there's no coming back. This is textbook astrophysics, a process observed and modeled for decades. But here's where things get strange. Not all black holes follow this script. Some seem to hit the brakes mid-collapse, as if something or someone hit the cosmic pause button. Take the case of certain supermassive black holes, like the one at the center of our own Milky Way. These behemoths, weighing millions or even billions of times the mass of our Sun, should be growing, devouring everything around them. Yet some appear oddly stable, as if they've reached some hidden equilibrium. Could their immense spin be counteracting gravity's pull? Or is there an unseen force at work, something we haven't yet accounted for in our equations? Then there's the mystery of intermediate mass black holes, cosmic middleweights that don't fit neatly into either stellar or supermassive categories. These elusive objects should, in theory, collapse just like their smaller or larger counterparts. But some linger in a strange twilight state, neither fully formed nor completely collapsed. It's as if the universe left them half-finished, taunting us with their incomplete existence. Even more puzzling are the rare black holes that seem to flicker, their event horizons wobbling like a mirage in the desert. These fluctuations suggest something turbulent is happening just beyond the edge, perhaps matter swirling in chaotic patterns or quantum effects playing havoc with spacetime itself. Whatever the cause, these anomalies force us to ask, do we really understand black holes at all? Or are we just scratching the surface of something far deeper and more mysterious? At the heart of Galaxy M87, a cosmic titan defies expectations. The supermassive black hole anchoring this distant galaxy should, by all known physics, be locked in an endless cycle of collapse and consumption. Yet when astronomers trained their telescopes on this behemoth, the same one that gave us humanity's first direct image of a black hole's shadow, they found something perplexing. Instead of the chaotic, unstable monster predicted by theory, it exhibited an eerie calm, as if suspended in cosmic equilibrium. One leading explanation points to the black hole's staggering spin. Imagine a figure skater pulling their arms in to accelerate, except here, the skater is a gravitational singularity rotating at nearly the speed of light. This extreme angular momentum might generate centrifugal forces powerful enough to counteract gravity's inward crush, creating a delicate balance between collapse and stability. It's like a cosmic tug of war where both sides are equally matched, leaving the black hole in a state of suspended animation, but spin alone might not tell the whole story. M87's black hole sits at the center of a bustling galactic metropolis, surrounded by swirling disks of gas and stars. The constant influx of matter, some of which gets ejected in powerful jets, could act like a counterweight, exerting outward pressure that stabilizes the black hole's structure. Think of it as a balloon being inflated from the inside while someone squeezes it from the outside. Under just the right conditions, the forces cancel each other out. This anomaly isn't just a curiosity, it challenges our fundamental assumptions about how black holes evolve. If angular momentum and external matter can halt collapse, what does that mean for other supermassive black holes across the universe? Could there be entire populations of these stubborn black holes, quietly resisting their predicted fates? The answers might rewrite textbooks, revealing that black holes aren't just simple cosmic trash compactors, but dynamic systems governed by subtle, unseen balances. And here's where it gets even stranger. Some theorists suggest that M87's black hole might be tapping into hidden reservoirs of dark energy or exotic physics at the quantum level. While still speculative, these ideas hint at a universe far more intricate than we've dared to imagine. Every observation of this cosmic rebel doesn't just deepen the mystery, it peels back another layer of reality, showing us how much we still have to learn. Somewhere in the cosmic shadows between the well-studied stellar black holes and their supermassive cousins lies a puzzling middle child, the intermediate mass black hole. These celestial oddballs, weighing anywhere from 100 to 100,000 times the mass of our Sun, should follow the same gravitational playbook as their larger and smaller siblings. Yet time and again they break the rules, pausing their collapse as if hitting an invisible cosmic speed bump. Take the curious case of HLX-1, a rogue intermediate black hole drifting through a distant galaxy. Discovered in 2009, this object defies classification. It's too massive to have formed from a single collapsing star, yet not hefty enough to anchor a galaxy like its supermassive counterparts. What's truly baffling is its behavior. Instead of steadily growing or collapsing further, it seems suspended in a strange equilibrium. Some researchers speculate it might be caught in a gravitational dance with unseen partners, while others propose it's feeding on hidden reservoirs of dark matter, creating a delicate balance between growth and decay. Then there's the peculiar population of intermediate black holes found in dense star clusters. These environments should be ideal for black hole mergers, where smaller black holes collide and combine into ever larger objects. Yet observations reveal something unexpected. Many of these black holes stall at intermediate masses, stubbornly refusing to grow larger. It's as if some cosmic checkpoint prevents them from graduating to supermassive status. Could intense gravitational interactions within these clusters be disrupting the normal collapse process? Or is there some fundamental limit to how quickly black holes can grow at these intermediate scales? The mystery deepens when we look at the energy signatures of these objects. Some intermediate black holes emit X-rays in irregular bursts rather than the steady streams we'd expect. These flickering patterns suggest their accretion disks, the swirling rings of superheated matter feeding the black hole, might be unstable or fragmented. One provocative theory suggests quantum effects near the event horizon could be creating microscopic speed bumps in spacetime itself, temporarily halting the inward flow of matter and energy. Perhaps most intriguing is the possibility that these black holes aren't actually paused. They might be transforming into something entirely different. Some theoretical models suggest intermediate black holes could be portals to exotic states of matter, where the crushing pressures inside trigger phase transitions we don't yet understand. Imagine water turning to ice, but instead it's spacetime itself crystallizing into some strange new form, creating a structure just rigid enough to resist total collapse. These anomalies don't just challenge our understanding of black holes, they force us to reconsider how all massive objects evolve in the universe. If black holes can stall midway through their life cycles, what other cosmic processes might have hidden pause buttons we haven't discovered yet? Each stubborn intermediate black hole is a cosmic laboratory, testing the limits of gravity and quantum physics in ways we're only beginning to comprehend. Dark matter, the universe's most elusive architect, might hold the key to black holes that refuse to collapse. Picture an invisible hand pressing against the fabric of spacetime, counteracting gravity's relentless crush. This isn't science fiction. It's one of the most compelling theories attempting to explain why some black holes defy expectations. Dark matter, which makes up roughly 85% of the universe's mass, doesn't interact with light or ordinary matter the way stars and planets do. But its gravitational pull is undeniable, shaping galaxies and bending the paths of light itself. Now, scientists suspect these mysterious halos could be propping up unstable black holes, creating cosmic standoffs where collapse should be inevitable. Take the case of certain supermassive black holes surrounded by dense clouds of dark matter. Simulations show that if enough dark matter accumulates around a black hole, its collective gravity could exert outward pressure, like an invisible scaffold holding up a collapsing building. The math suggests something remarkable under the right conditions. This balance could stall a black hole's collapse indefinitely. Imagine a tug of war where dark matter's invisible threads pull just hard enough to keep gravity from winning. But how would this work in practice? One hypothesis points to the way dark matter behaves near black holes. Unlike normal matter, which gets shredded into hot, glowing disks as it falls inward, dark matter might orbit in vast, diffuse clouds. These clouds could act like a buffer, absorbing and redistributing gravitational energy in ways that stabilize the black hole's structure. It's akin to how a tightly packed crowd can absorb the force of a pushing match, preventing anyone from toppling over. The implications are staggering. If dark matter truly influences black hole stability, it would forge an unprecedented link between two of astrophysics' greatest mysteries. We might finally understand why some supermassive black holes stop growing despite sitting in matter-rich environments. Their dark matter halos could be hitting the brakes. Even more tantalizing is the possibility that dark matter itself could take on exotic forms near black holes, perhaps crystallizing into quantum states we've never observed. Yet not all researchers are convinced. Skeptics argue that dark matter's gravity, while pervasive, might not be concentrated enough to halt collapse on its own. Others propose alternative explanations like hidden magnetic fields or chaotic gas inflows that could mimic dark matter's effects. The debate highlights how much we still don't know about dark matter, black holes, and the strange dance between them. What's clear is that every anomaly, every black hole that lingers when it should collapse offers a clue. Future telescopes designed to map dark matter's distribution could test these ideas, revealing whether these invisible halos are cosmic peacekeepers, quietly maintaining balance in the universe's most violent neighborhoods. Until then, the mystery remains, a reminder that the cosmos still has secrets to spill. At the quantum level, reality behaves in ways that defy common sense, particles popping in and out of existence, objects existing in multiple states at once. Now imagine these bizarre rules applying to the most extreme objects in the universe, black holes. According to classical physics, a collapsing black hole should crush down to an infinitely dense point called a singularity. But quantum mechanics whispers a different story, one where the very fabric of spacetime might rebel against this fate, creating a strange, frothy barrier known as quantum fuzz that could halt total collapse. This idea stems from the fiery marriage of quantum theory and gravity, two fundamental forces that have resisted unification for over a century. In ordinary circumstances, gravity dominates on cosmic scales while quantum effects rule the subatomic world. But inside a black hole where matter is compressed to unimaginable densities, these realms collide. Theories like loop quantum gravity suggest that spacetime itself might be granular at the tiniest scales, woven from indivisible threads a billion trillion times smaller than an atom. Near a black hole's core, this granularity could prevent infinite collapse, like a microscopic safety net catching spacetime before it tears apart. Picture this quantum fuzz as a seething ocean of virtual particles, constantly forming and annihilating at the event horizon. Some models propose that these particles don't just vanish, they leave behind faint imprints, a kind of quantum memory that subtly alters the black hole's structure. Over time, this could build up enough pressure to counteract gravity's inward pull, stabilizing the black hole in a precarious equilibrium. It's as if the universe has a built-in failsafe, preventing its most destructive objects from reaching total annihilation. The implications ripple far beyond black holes. If quantum fuzz exists, it could resolve one of physics' most vexing paradoxes, the black hole information problem. Stephen Hawking showed that black holes slowly evaporate, seemingly erasing information about what fell into them. But quantum mechanics insists information can't be destroyed. Quantum fuzz might preserve that information in its chaotic churn, encoding it in the black hole's surface like a cosmic hard drive. This would mean black holes aren't the ultimate shredders we once thought, but complex, dynamic systems obeying deeper quantum laws. Not everyone is convinced, of course. Critics argue that quantum gravity remains untested, its mathematics too abstract to confirm without observational evidence. Others propose competing ideas, like black holes tunneling into entirely new universes through quantum fluctuations. Yet even these alternatives share a common thread, the recognition that quantum mechanics must fundamentally alter our picture of black hole interiors. Every anomaly, every stubborn black hole that refuses to collapse might be a clue pointing toward this quantum revolution. What's exhilarating is that we might not have to wait long for answers. Next-generation gravitational wave detectors could catch whispers of quantum fuzz in the echoes of colliding black holes. Certain patterns in these ripples might betray the presence of exotic structures near event horizons, offering the first direct hints of quantum gravity in action. For now, these ideas live at the edge of theory and imagination. But in a universe where the smallest particles hold sway over the largest cosmic beasts, anything seems possible. Some black holes don't just bend the rules, they tear them up entirely. Imagine an event horizon, that infamous boundary of no return, flickering like a candle in the wind. This isn't theoretical. Astronomers have observed black holes where the edge wobbles unpredictably, as if the fabric of space-time itself is struggling to keep its shape. These erratic event horizons defy the smooth, stable structures predicted by Einstein's theory of relativity, hinting at forces we've yet to fully understand. One possible culprit lies in the chaos of accretion disks, the superheated maelstroms of gas and dust spiraling into black holes. Normally, these disks behave like orderly whirlpools, but under extreme conditions, they can become turbulent, with clumps of matter crashing into each other like cars in a cosmic traffic jam. This turbulence might send shockwaves rippling through spacetime, distorting the event horizon in ways that make it appear to pulsate or even temporarily shrink. Picture a pond's surface during a rainstorm, with each droplet creating ripples that overlap and interfere, except here, the pond is the edge of reality, and the raindrops are chunks of matter moving at nearly the speed of light. But accretion disks alone might not explain the most extreme fluctuations. Some theorists point to quantum phenomena occurring just beyond the event horizon. According to quantum mechanics, empty space is anything but empty. It's a seething foam of virtual particles that blink in and out of existence. Near a black hole, these particles might interact in strange ways, creating microscopic instabilities that amplify into visible horizon distortions. It's as if the quantum noise of the universe is leaking through, making the black hole's boundary shimmer like a mirage. Even more intriguing is the possibility that these wobbling event horizons are signs of something deeper, a black hole's internal structure fighting against collapse. Some models suggest that the singularity at a black hole's core might not be a single point but a dynamic, ever-changing region where matter and energy rebound in exotic ways. If true, these internal convulsions could send gravitational echoes rippling outward, warping the event horizon from the inside out. Think of it like a bell vibrating after being struck. The event horizon might be ringing with the aftershocks of a collapse that wasn't quite complete. The stakes are higher than they seem. If we can decode these erratic horizons, we might finally bridge the gap between relativity and quantum mechanics, two pillars of physics that have resisted unification for a century. Black holes with unstable edges could be cosmic Rosetta Stones, offering clues to how gravity behaves at the smallest scales. Future gravitational wave detectors, like the Laser Interferometer Space Antenna, might catch these fluctuations in action, turning theoretical curiosities into observable phenomena. For now, each flickering event horizon is a puzzle waiting to be solved. Whether the cause is turbulent matter, quantum froth, or something even stranger, one thing is clear: black holes aren't the static monsters we once imagined. They're alive with hidden dynamics, whispering secrets about the universe's most fundamental laws, if only we learn how to listen. Stephen Hawking's most unsettling revelation wasn't about how black holes behave, it was about what they might erase. In the 1970s, he showed that black holes slowly leak energy, evaporating over cosmic timescales. But here's the catch: according to his math, all the information about what fell into the black hole, every atom, every particle, every shred of cosmic history, should vanish forever when the black hole finally dies. This idea, known as the information paradox, sent shockwaves through physics because it violates a fundamental rule of quantum mechanics: information can never be truly destroyed. Now imagine this paradox colliding with the mystery of black holes that refuse to collapse. Could the preservation of information somehow be tied to these cosmic anomalies? Think of a black hole not as a cosmic shredder, but as a scrambled hard drive. Even if data gets fragmented, the underlying information still exists. It's just encoded in ways we can't easily read. Some theories suggest that black holes might work similarly, with information imprinted on their event horizons like a hologram. This holographic principle implies that what happens inside a black hole isn't lost, it's projected onto its surface in a quantum code we don't yet understand. If true, this could mean that the energy required to preserve information exerts a subtle back pressure, like a cosmic archivist fighting against gravity's destructive pull. But how might this play out in black holes that resist collapse? One provocative idea is that information preservation could alter the very fabric of space-time near the singularity. Quantum corrections, tiny adjustments to Einstein's equations, might create a kind of repulsive force at ultra-small scales, preventing total collapse. Picture a spring compressed to its limit. At some point it pushes back. In this case, the spring is space-time itself, resisting infinite compression to safeguard the information trapped within. The implications ripple far beyond theoretical puzzles. If information survival stabilizes black holes, it could explain why some seem to hover in partial collapse, their event horizons flickering like faulty neon signs. Observations of gravitational waves from merging black holes might already hold clues. Certain echo-like patterns in the signals could hint at information being smeared across the horizon during collisions. Future detectors like the Einstein telescope could hunt for these fingerprints, offering the first experimental evidence that black holes are cosmic librarians as much as cosmic destroyers. Yet the debate is far from settled. Skeptics argue that information preservation might not directly impact collapse dynamics. It could be a side effect rather than a cause. Others propose wilder alternatives, like black holes birthing new universes where the information reemerges. What's clear is that every stubborn black hole, every anomaly that defies expectations, forces us to confront a deeper truth. The universe might be far more inventive at preserving its secrets than we ever imagined. And that changes everything. Long before the first stars flickered to life in the universe's chaotic infancy, a different kind of black hole may have been born, not from dying stars but from the raw turbulence of creation itself. These are primordial black holes, hypothetical relics forged in the seething density of the Big Bang's aftermath. Unlike their stellar descendants, which form from collapsing stars, primordial black holes could be as small as a pinhead or as massive as 1,000 suns, their size dictated by random fluctuations in the infant cosmos. What makes them truly extraordinary isn't just their origin, it's the tantalizing possibility that some might still exist today, lurking in the darkness like cosmic fossils. The survival of these ancient objects hinges on conditions we can barely imagine. In the first seconds after the Big Bang, pockets of space may have been so densely packed that they collapsed directly into black holes, bypassing the need for a star's death throes. Without the violent turbulence of a supernova, these black holes might have formed with peculiar properties, perhaps ultra-smooth event horizons or exotic internal structures that slowed their evaporation. Some theories even suggest they could have grown microscopic quantum armor in those early moments, a protective effect from the extreme physics of the young universe that halted further collapse. If true, this would mean primordial black holes aren't just curiosities, they could be time capsules, preserving secrets about the universe's first moments. Their potential impact on modern cosmology is staggering. Take dark matter, the invisible glue holding galaxies together. If primordial black holes exist in vast numbers, they might account for some, or even all of this mysterious substance. Imagine the Milky Way's halo not as a cloud of unknown particles, but as a swarm of ancient black holes, each no larger than a mountain yet weighing as much as a planet. Recent observations of unexpected gravitational lensing events, where distant stars briefly brighten as unseen objects pass in front of them, could hint at this very scenario. These fleeting flashes might be the footprints of primordial black holes drifting silently through our galaxy, but the evidence remains frustratingly elusive. Some researchers argue that if primordial black holes were abundant, we'd see more obvious signs like frequent bursts of Hawking radiation as the smallest ones evaporated. Others counter that certain mass ranges could have avoided detection entirely, hiding in plain sight. The debate turns even more intriguing when considering bizarre outliers like the so-called ogle microlensing events, unexplained anomalies where stars flicker in ways that don't match known objects. Could these be primordial black holes with unusual orbits or compositions? Perhaps the most mind-bending possibility is that some primordial black holes didn't just survive, they thrived. A handful could have grown into the supermassive black holes anchoring galaxies today, skipping the usual growth process entirely. This would rewrite the cosmic playbook, suggesting that some black holes didn't evolve from stars but were born ready-made in the universe's first moments. Future telescopes like the Vera Rubin Observatory might finally settle the debate by mapping the sky with unprecedented precision, hunting for the telltale distortions caused by these ancient wanderers. Whether they're out there or not, primordial black holes force us to confront profound questions. If they exist, they're a living link to the Big Bang, a reminder that the universe's earliest instance might still echo in the darkness. If they don't, their absence is equally revealing, narrowing down the possible ways our cosmos could have taken shape. Either way, the hunt for these relics isn't just about black holes, it's about decoding the universe's first whispers. What if everything we thought we knew about black holes was upside down? The holographic principle turns our intuition inside out by suggesting that the true nature of a black hole isn't hidden deep within its inky depths, but written across its surface like a cosmic tattoo. This radical idea emerged from string theory and quantum gravity research, proposing that all the information about what falls into a black hole gets encoded in two-dimensional patterns on its event horizon. Think of it like a hologram, a flat surface containing all the data needed to reconstruct a three-dimensional scene. But here's where it gets wild. If black holes store information this way, it might fundamentally change how they collapse. Picture a collapsing star nearing the point of becoming a black hole. According to classical physics, it should crush down indefinitely. But the holographic principle introduces quantum information theory into the mix, where every particle's data must be preserved. As matter approaches the event horizon, its information could get smeared across the surface rather than disappearing inward. This creates an information paradox of a different kind, not about loss, but about storage capacity. The event horizon might become so densely packed with quantum bits that it resists further compression, like a hard drive that refuses to be overwritten. Some theorists calculate that this information pressure could counteract gravity's pull, effectively putting the brakes on total collapse. The math behind this is both elegant and mind-bending. The holographic principle suggests a deep connection between surface area and entropy, the measure of disorder in a system. A black hole's entropy turns out to be proportional to its event horizon's area, not its volume. This implies that the maximum information any region of space can hold depends on its boundary, not its interior. If correct, it would mean black holes are nature's ultimate information storage devices, with their two-dimensional surfaces encoding everything about their three-dimensional content. But how does this translate to real black holes in space? Observations of merging black holes through gravitational wave astronomy might hold clues. When two black holes collide, their event horizons ripple and merge in ways that could reveal whether information is truly preserved on their surfaces. Certain patterns in the gravitational wave signals, like subtle echoes or unexpected frequency shifts, might betray the presence of holographic encoding at work. These minute details could distinguish between a conventional collapsing singularity and a black hole stabilized by quantum information pressure. Not everyone is convinced. Critics argue that the holographic principle remains untested, its predictions too subtle to confirm with current technology. Some propose alternative explanations, like modified theories of gravity that eliminate singularities without invoking quantum information storage. Others caution that the principle might apply only to certain types of black holes, leaving others to collapse normally. The debate highlights how much we still don't understand about the intersection of gravity, quantum mechanics, and information theory. What's undeniable is the principle's philosophical impact. If black holes truly are holograms, it suggests reality itself might operate similarly, with our three-dimensional universe being a projection from some deeper, two-dimensional structure at its boundaries. This isn't just about black holes anymore, it's about the fundamental nature of space-time and information. Every black hole that resists collapse could be a laboratory for testing these ideas, offering glimpses into a unified theory that has eluded physicists for generations. The implications ripple outward. If the holographic principle holds, it would mean black holes aren't cosmic dead ends but dynamic systems where gravity and quantum information achieve an uneasy truce. Their event horizons might not be mere boundaries, but active participants in the universe's information economy, places where the rules of reality get rewritten in quantum code. As we peer deeper into these mysteries, each stubborn black hole becomes more than an anomaly. It's a cipher waiting to be decoded, holding secrets about how information, space, and time intertwine at the most fundamental level. Black holes might be sporting a bizarre cosmic hairdo, and no, we're not talking about the swirling gas of their accretion disks. The term soft hair comes from a radical theory proposing that black holes could be surrounded by ultra-faint quantum fields, lingering like whispers at the edges of their event horizons. These aren't physical strands, of course, but subtle imprints left by particles and energy, a kind of quantum memory that might hold the key to why some black holes resist total collapse. The idea builds on a decades-old puzzle. What happens to the information swallowed by a black hole? Stephen Hawking's calculations suggested it vanishes forever, but quantum physics insists information can't be destroyed. In 2016, physicists Andrew Strominger and Hawking himself proposed a middle ground. They theorized that when matter falls into a black hole, it leaves behind faint traces in the form of zero-energy photons or gravitons particles so weak they barely interact with anything. These particles, dubbed soft hair, would cling to the event horizon, encoding details about what fell in without significantly altering the black hole's gravity or structure. Here's where it gets fascinating. If soft hair exists, it could act like a cosmic ledger, subtly redistributing energy near the event horizon. Over time, this might create minute imbalances, tiny pushes and pulls that counteract the relentless inward crush of gravity. Picture a sheet of paper held up by a gentle breeze. The force is barely noticeable, but under just the right conditions, it could be enough to keep the paper aloft. Similarly, soft hair's delicate influence might stabilize certain black holes, preventing them from collapsing into singularities as expected, but not everyone is convinced. Critics point out that soft hair's effects would be vanishingly small, perhaps too weak to meaningfully alter a black hole's fate. Others argue that the theory relies on untested assumptions about how quantum fields behave in extreme gravity. The debate took an unexpected turn when researchers analyzing gravitational wave data from black hole mergers reported hints of echoes in the signal's ripples that could match predictions of soft hair's presence. Yet follow-up studies found no conclusive evidence, leaving the theory in limbo. What's at stake isn't just an academic curiosity. If soft hair exists, it could solve the information paradox while offering a new lens on black hole stability. It might also hint at deeper connections between quantum mechanics and gravity, two forces that have resisted unification for over a century. Future experiments like next-generation gravitational wave detectors or quantum simulations could finally test these ideas, revealing whether black holes truly wear these quantum strands, or if the universe's mysteries remain tightly coiled, waiting to be unraveled. Deep within the swirling chaos of a black hole's grasp, another invisible force wages war against gravity's relentless pull, magnetism. While we often picture black holes as simple cosmic vacuum cleaners, the reality is far more complex, especially when powerful magnetic fields enter the equation. These fields, generated by the frenzied motion of charged particles in accretion disks, can grow so intense that they rival gravity itself, creating a precarious balance where collapse stalls. Picture a cosmic tug-of-war where one team is gravity, dragging matter inward, and the other is magnetism, pushing back with equal ferocity. Some of the most compelling evidence comes from active galactic nuclei, where supermassive black holes spew jets of plasma thousands of light-years into space. These jets are sculpted and accelerated by magnetic fields so strong they can twist spacetime itself. In systems like the famous Blazar-Markarian 501, observations reveal magnetic fields channeling energy outward, acting like cosmic shock absorbers that stabilize the black hole's feeding process. It's as if the black hole has built-in stabilizers, preventing it from gorging itself into instability. But how exactly do magnetic fields achieve this balancing act? One theory points to the way these fields thread through the accretion disk, creating zones of pressure that act like scaffolding. As matter spirals toward the event horizon, the magnetic fields become tightly wound, storing immense energy. At a critical point, this energy can erupt outward, propelling material away in jets while simultaneously relieving the inward pressure that would otherwise drive collapse. Think of it like a pressure valve on a boiler. The magnetic fields release just enough energy to keep the system from exploding or imploding. Not all magnetized black holes behave the same way, though. Some, like the one at the heart of galaxy Cygnus A, display erratic outbursts where magnetic fields seem to flicker and reconfigure. These fluctuations suggest that the equilibrium is fragile, a dynamic dance rather than a static standoff. Simulations show that under certain conditions, magnetic fields can even fracture, creating temporary gaps where gravity briefly gains the upper hand before magnetism rebounds. This might explain why some black holes appear to teeter on the edge of collapse without ever fully succumbing. The broader implications are staggering. If magnetic fields can regulate black hole growth, they might also explain why supermassive black holes don't grow indefinitely despite sitting in galaxies brimming with fuel. These fields could be cosmic regulators, ensuring black holes evolve in harmony with their surroundings. Future missions like the European Space Agency's Athena X-ray Observatory aim to map these magnetic structures in unprecedented detail, potentially revealing whether they're the hidden architects behind some of the universe's most persistent black hole anomalies. Yet mysteries remain. Why do some black holes develop such powerful magnetism while others seem comparatively quiet? Could there be a threshold where magnetic fields become strong enough to halt collapse entirely, or do they merely delay the inevitable? Each observation peels back another layer, showing us that black holes aren't just prisoners of gravity. They're players in a far richer cosmic drama, where magnetism, turbulence, and quantum effects all vie for control. And in that struggle, we might find the answers to why some black holes stubbornly refuse to follow the rules. In the cosmic dance of binary black holes, something extraordinary happens. Gravity's grand finale doesn't always go as planned. When these massive partners spiral toward each other, their merger should, in theory, result in a single, perfectly spherical black hole. Yet simulations and gravitational wave observations reveal a puzzling twist. Some collisions leave behind a distorted remnant, a black hole that wobbles like a top losing speed, its shape warped as if the collapse was abruptly interrupted. It's as if the universe hit pause on its own destruction, leaving behind a cosmic fingerprint that defies expectations. The secret may lie in the chaotic interplay of their orbits. As two black holes circle each other, their mutual gravity creates tidal forces powerful enough to stretch spacetime itself. These forces don't just pull matter inward, they also transfer energy between the black holes, like a pendulum passing momentum back and forth. In some cases, this energy exchange can temporarily counteract the inward pull of collapse, slowing the process like a cosmic buffer. Picture two ice skaters spinning while clasping hands. If their movements sync just right, they can balance each other's momentum, delaying the inevitable fall. Similarly, binary black holes might stabilize each other long enough to leave behind a misshapen remnant rather than a smooth singularity. Gravitational wave detectors like LIGO and Virgo have already glimpsed hints of this phenomenon. In 2019, a merger dubbed GW190521 produced a black hole with an unusually long ring down, the faint after ripple of spacetime settling into a new shape. Instead of the clean, quick decay predicted for a spherical remnant, the signal wobbled, suggesting the final black hole was still vibrating, its structure uneven. Some researchers argue this could be a smoking gun for delayed collapse, where the merged object hasn't fully settled into its final form, but the implications stretch far beyond a single oddball observation. If binary mergers routinely produce these distorted remnants, it could force us to rethink how gravitational waves are interpreted. Current models assume clean, spherical black holes post-merger, an approximation that works for most detections. But what if a significant fraction of collisions leave behind lumpy, unstable objects? Their gravitational waves would carry hidden signatures of incomplete collapse, like echoes of the chaos that created them. Future detectors with higher sensitivity might uncover a whole zoo of these exotic remnants, revealing how often black holes defy the textbook endings. The mystery deepens when we consider what's happening inside these remnants. One radical possibility is that the merger's violence triggers a temporary phase transition, where the collapsing matter shifts into an exotic state like water freezing into ice before fully succumbing to gravity. Certain string theory models suggest that under such extreme conditions, the singularity might be replaced by a dense knot of higher dimensional strings, effectively hitting a quantum speed bump on the way to total collapse. While speculative, these ideas highlight how much we still don't understand about the final moments of a black hole's birth. For astrophysicists, these anomalies aren't just quirks, they're opportunities. Every distorted remnant, every delayed collapse, is a natural laboratory for testing gravity's limits. By studying these systems, we might catch glimpses of physics beyond Einstein's theory, where quantum effects and extra dimensions leave their mark on spacetime itself. The next generation of observatories, like the space-based LISA mission, could detect thousands more mergers, building a census of black hole behavior that either confirms these anomalies or sends theorists back to the drawing board. One thing is certain, the universe loves to surprise us. Just when we think we've figured out the rules, binary black holes whisper a different story. one where collapse isn't always inevitable, and where the darkest objects in the cosmos might hold the brightest clues to reality's deepest secrets. At the farthest edges of theoretical physics lies a concept so strange it bends reality itself: exotic matter. Unlike the ordinary stuff making up stars and planets, exotic matter defies intuition, possessing negative energy or pressure that could push against gravity rather than yielding to it. Picture trying to inflate a balloon where the rubber pulls inward instead of stretching outward. That's the kind of counterintuitive behavior we're talking about. While no one has ever observed this material directly, its hypothetical existence could solve one of black hole science's stickiest problems: why some of these cosmic monsters seem to freeze mid-collapse, as if an invisible hand pressed pause on their demise. The math behind this idea traces back to Einstein's equations, which allow for solutions where matter behaves in bizarre ways. One such solution, known as dark energy, the mysterious force accelerating the universe's expansion, hints that negative pressure isn't just possible, it might dominate the cosmos. Apply that logic to black holes and you get a tantalizing possibility. If enough exotic matter accumulated near a singularity, its repulsive effect could balance gravity's inward crush. It's like stuffing a collapsing building with endless springs, each one pushing back just hard enough to keep the structure from imploding. Some of the most dramatic implications emerge from wormhole research, where exotic matter is often invoked to prop open tunnels through space-time. The same principles might stabilize black holes, creating regions where collapse stalls indefinitely. Imagine a black hole's core not as a singularity, but as a dense knot of this peculiar substance, generating enough outward pressure to halt further compression. Simulations of such scenarios produce objects that look like black holes from the outside, complete with event horizons, but harbor exotic interiors that defy classical predictions. These gravastars, as they're nicknamed, could explain why certain black holes emit unusual radiation patterns or exhibit unexpected stability. Yet the challenges are as vast as the ideas are bold. For one, exotic matter violates what physicists call the null energy condition, a bedrock assumption that energy densities can't dip below zero. While quantum mechanics permits temporary violations of this rule through phenomena like the Casimir effect, where quantum fluctuations create negative energy between closely spaced plates, sustaining enough exotic matter to stabilize a black hole would require engineering far beyond anything nature has shown us. Skeptics argue that even if such matter exists, it might be inherently unstable, collapsing into non-existence before it could influence a black hole's fate. The debate takes a wilder turn when string theory enters the picture. Some models suggest that higher dimensional branes, hypothetical objects from string theory, could mimic exotic matter's effects, creating stabilized black holes without needing negative energy at all. Others propose that the vacuum of space itself might undergo phase transitions near black holes, temporarily generating exotic properties that resist collapse. These ideas, while speculative, highlight how creatively physicists must think when grappling with anomalies that refuse to fit the standard mold. What's thrilling is that we might not need to wait for futuristic technology to test these ideas. Gravitational wave astronomy could soon provide clues. Certain echoes or frequency shifts in merger signals might betray the presence of exotic matter's influence. Even more provocative are hints from quantum experiments, where lab-made analogs of black holes exhibit behaviors eerily reminiscent of exotic stabilization. While these aren't proof, they're tantalizing breadcrumbs, suggesting nature might be more inventive than we've dared to imagine. Whether exotic matter truly exists or remains a mathematical curiosity, its exploration reshapes our understanding of black holes' possible fates. These cosmic rebels, resisting collapse against all odds, force us to confront the limits of known physics and the exhilarating prospect that the universe's rulebook might have chapters we've yet to read. Every anomaly, every stubborn black hole that lingers where none should, whispers the same question: what if the most exotic stuff in the cosmos isn't just theoretical after all? What if our universe isn't the whole story? String theory, one of physics' most ambitious frameworks, suggests that reality might extend beyond the three dimensions we experience: height, width, and depth, into hidden spatial realms curled up so tightly we've never detected them. These extra dimensions could rewrite the rules for black holes, turning them from cosmic vacuum cleaners into something far stranger. Imagine a black hole not as a sphere, but as a higher dimensional shape, its gravity leaking into unseen directions. In such a universe, collapse might not be inevitable. It could depend on how many dimensions the black hole calls home. The math behind this idea is both elegant and mind-bending. In our familiar three-dimensional world, gravity follows Isaac Newton's inverse square law, weakening predictably with distance, but add extra dimensions and gravity's behavior changes dramatically. Some models suggest it could drop off faster or slower, altering how black holes form and evolve. A higher dimensional black hole might dissipate its energy across these hidden directions, like water soaking into a sponge, reducing the crushing forces that drive collapse. It's as if the black hole has escape routes we can't see, bleeding off pressure into dimensions beyond our perception. This isn't just speculation, it has observable consequences. If higher dimensional black holes exist, they'd evaporate differently than their three-dimensional cousins. Hawking radiation, the faint glow of particles escaping black holes, would carry signatures of these extra dimensions, potentially detectable by future telescopes. Even more striking, collisions between higher dimensional black holes could produce gravitational waves with unique frequencies, like cosmic drumbeats echoing through the fabric of spacetime. The Laser Interferometer Space Antenna, set to launch in the 2030s, might catch these whispers, offering the first direct evidence that black holes are playing by different rules in unseen realms. But the implications go deeper than detection. Some theories propose that in higher dimensions, singularities, the infinitely dense points at black holes' cores, might not form at all. Instead, matter could reach a state of maximum density before rebounding or settling into a stable, finite structure. Picture a ball of yarn unraveling into extra dimensions, its threads spreading out rather than knotting into a single point. This could explain why some black holes appear to resist total collapse, their event horizons flickering like faulty lights. They might be higher dimensional objects intruding into our three-dimensional world, their true nature hidden just beyond our view. The most radical versions of this idea come from string theories, brain world scenarios, where our universe is a three-dimensional membrane floating in a higher dimensional bulk. In such models, black holes could be tangled knots of spacetime piercing through multiple branes, their gravity shared across parallel universes. Collapse in one dimension might be offset by expansion in another, creating equilibrium states that defy conventional physics. While this sounds like science fiction, the math checks out, and if correct, it would mean black holes aren't just cosmic anomalies, but bridges to realities we've yet to imagine. Skeptics, of course, point out the lack of direct evidence. Extra dimensions remain theoretical, and no experiment has yet confirmed their existence. But the persistence of black holes that refuse to collapse, along with oddities in particle collisions at the Large Hadron Collider, hints that something unusual might be at work. Whether these anomalies stem from higher dimensions or another undiscovered mechanism, one thing is clear: the universe still holds cards it hasn't shown us. Every stubborn black hole, every gravitational glitch, could be a clue pointing toward a grander cosmic architecture, one where the dimensions we see are just the beginning. The event horizon of a black hole has always been imagined as a silent, invisible boundary, a point of no return where the laws of physics quietly surrender to the unknown. But what if that boundary isn't so placid? What if crossing it doesn't mean slipping gently into darkness, but plunging into a blistering inferno? This is the essence of the Firewall Paradox, a theory so radical it upends decades of assumptions about what happens at the edge of a black hole. According to this idea, the event horizon might not be smooth and featureless. It could be a raging wall of high-energy particles, a cosmic minefield where matter isn't just crushed, but incinerated on contact. The paradox emerged from an attempt to reconcile two seemingly incompatible truths: quantum mechanics, which insists information can never be destroyed, and general relativity, which suggests anything crossing a black hole's horizon is lost forever. In 2012, physicists Ahmed Almary, Donald Maroff, Joe Polchinski, and James Sully proposed a startling solution. Perhaps the event horizon isn't a passive gateway, but a fiery barrier that burns up incoming material, preserving its information in the process. Imagine tossing a book into a black hole. Instead of vanishing into oblivion, its pages might be shredded and scattered across the horizon as a burst of encoded energy, like words etched into the surface of a bonfire. This isn't just a thought experiment. If firewalls exist, they could fundamentally alter how black holes collapse. Normally, gravity's pull grows stronger as you approach the singularity, compressing matter without resistance. But a firewall would introduce a violent counterforce, like a cosmic blowtorch pushing back against the inward crush. The energy released at the horizon might create enough outward pressure to stall collapse, at least temporarily, turning the black hole's interior into a turbulent battleground between gravity and quantum fire. Some models even suggest that under the right conditions, this equilibrium could stabilize the black hole, preventing it from reaching a true singularity. Yet the theory remains fiercely controversial. Critics argue that firewalls violate Einstein's equivalence principle, which states that free-falling observers shouldn't detect extreme forces as they cross the horizon. A firewall would make black holes less like gentle cosmic pits and more like lethal traps, contradicting the smooth spacetime predicted by relativity. Others point out that the paradox might reveal a deeper flaw in our theories, a sign that we're missing a crucial piece of the puzzle that unites quantum mechanics and gravity. Intriguingly, the debate isn't purely academic. Gravitational wave observatories might soon detect subtle hints of firewalls in the ring-down signals of merging black holes. Certain distortions in these ripples could indicate whether horizons are smooth or seething with quantum fury. Meanwhile, lab experiments using ultra-cold atoms to simulate black hole physics have observed firewall-like effects, where simulated horizons suddenly erupt with energy. These aren't perfect analogs, but they suggest nature might allow such extreme phenomena under the right conditions. Whether firewalls are real or not, their very possibility forces us to confront unsettling questions. If black holes can harbor such violent boundaries, what other surprises might lurk in their depths? Could these fiery horizons be nature's way of preventing total collapse, or are they merely symptoms of a deeper instability we don't yet understand? Every anomaly, every stubborn black hole that refuses to follow the rules, reminds us that the universe's most extreme environments might still be hiding secrets no one has dared to imagine. Gravitational waves aren't just ripples in space-time, they're cosmic messengers, carrying secrets from the universe's most violent events. But some black holes don't just send a single signal, they whisper in echoes, repeating their gravitational murmurs like a distant drumbeat bouncing off invisible walls. These strange reverberations, first spotted in data from the LIGO and Virgo observatories, suggest there's more to black holes than a simple event horizon and a crushing singularity. Instead, they hint at hidden structures lurking just beyond the edge, as if the black hole's surface is textured with quantum bumps or surrounded by a ghostly membrane we can't yet see. Take the case of GW19-00421, a black hole merger detected in 2019. As the newly formed black hole settled into its final state, physicists expected the gravitational wave signal to fade smoothly, a phenomenon called ring-down. Instead, the data revealed faint but distinct echoes, repeating at intervals that defied conventional models. It was as if the gravitational waves were ricocheting off something unseen, like sound bouncing between canyon walls. One explanation: the event horizon might not be the ultimate boundary we thought it was. Some theories propose a quantum halo, or firewall, just outside the horizon, a region where spacetime itself becomes frothy with microscopic turbulence. These structures could act like cosmic mirrors, reflecting gravitational waves back inward and creating the eerie echoes we detect. Not everyone agrees on what's causing these echoes, though. Skeptics argue they could be artifacts in the data, glitches or noise masquerading as signals. Others suggest less exotic explanations, like debris from the collision swirling around the newborn black hole, creating temporary barriers that scatter gravitational waves. But the most tantalizing interpretation ties back to the black hole information paradox. If information isn't truly lost when matter falls into a black hole, perhaps it leaves traces in these echoes, encoded in the timing and amplitude of the repeating waves. Imagine each echo as a fragment of a cosmic puzzle, preserving details about what fell in long after the event horizon sealed shut. The stakes couldn't be higher. If echoes are real, they might be our first direct evidence of quantum gravity, the elusive theory bridging Einstein's relativity with the quantum world. Certain models, like loop quantum gravity or string theory, predict spacetime becomes granular at the smallest scales, and these granular structures could generate the very echoes we're detecting. Future observatories like the Einstein Telescope or the space-based LISA mission will listen for these whispers with unprecedented precision, potentially confirming whether black holes have secret layers beyond their event horizons. What's fascinating is how these echoes blur the line between destruction and preservation. A black hole might not be the ultimate eraser of information. After all, it could be a cosmic archivist, storing data in its gravitational reverberations. Every echo we detect is a clue, a hint that the universe's most enigmatic objects are far more complex than we ever imagined. And as we tune our instruments to these ghostly signals, we're not just studying black holes, we're decoding the very fabric of reality, one echo at a time. The universe isn't just expanding, it's accelerating, stretching spacetime itself at an ever-increasing rate. This cosmic expansion, driven by the mysterious force we call dark energy, might be doing more than just pushing galaxies apart. It could be subtly reshaping the fate of black holes, those gravitational titans we once thought were immune to the universe's grand dynamics. Picture a black hole sitting in the vastness of space, not just pulling matter inward, but also feeling the faint, relentless tug of the cosmos stretching around it. Over billions of years, this expansion might act like an invisible hand, gently prying at the black hole's structure, altering how, or even if, it collapses. At first glance, the idea seems counterintuitive. Black holes are the ultimate gravitational traps, their pull so strong that not even light can escape. How could something as diffuse as cosmic expansion compete with that? The answer lies in the subtle interplay between gravity and the large-scale geometry of the universe. As space expands, it creates a kind of outward pressure, a stretching force that pervades every corner of the cosmos. For most objects, like stars or planets, this effect is negligible. Their gravity easily overpowers it. But for black holes, especially those in the loneliest reaches of intergalactic space, the cumulative effect over eons might be significant. Imagine a rubber sheet being stretched in all directions. Even a heavy weight on that sheet would eventually feel the tension, its position ever so slightly shifted. The math behind this is fascinating. Some theoretical models suggest that in an accelerating universe, the event horizon of a black hole, the point of no return, could slowly grow larger, not because the black hole is gaining mass, but because the expansion of space itself is altering its gravitational influence. It's as if the black hole's reach is being stretched by the universe's expansion, creating a delicate balance between the inward pull of gravity and the outward stretch of spacetime. In extreme cases, this could lead to a phenomenon called cosmic baldness, where the black hole's outer layers are slowly pulled apart, leaving behind a naked singularity, a theoretical object without an event horizon visible to the outside universe. But the implications go even deeper. If cosmic expansion affects black hole collapse, it could mean that the universe's fate is intertwined with the life cycles of its darkest objects. In a hypothetical far future where dark energy dominates completely, some models predict that even black holes might eventually evaporate, not through Hawking radiation, but through the relentless stretching of spacetime. The universe's expansion could grow so intense that it tears apart the very fabric of black holes, dissolving them into the void. It's a poetic symmetry. The same force that drives the cosmos apart might also be the one that finally unravels its most indestructible objects. Yet not all researchers are convinced. Critics argue that the effect of cosmic expansion on black holes, while real in theory, would be vanishingly small on any timescale we can observe. After all, the universe's acceleration is subtle, measurable only over cosmic distances and epochs. For a black hole, local gravity would always dominate, making any expansion-driven changes negligible in practice. Others counter that in regions of the universe with unusually low matter density, cosmic voids where dark energy reigns supreme, the effect might be more pronounced, creating black holes that behave unlike any we've seen. The debate highlights how much we still don't understand about the interplay between gravity and cosmic expansion. Every observation of distant black holes, every subtle anomaly in their behavior, could be a clue to this hidden relationship. Future telescopes like the Vera Rubin Observatory or the James Webb Space Telescope might catch glimpses of black holes in these extreme environments, testing whether the universe's expansion leaves its mark on them. Until then, the idea remains a tantalizing possibility, a reminder that even the mightiest objects in the cosmos aren't isolated from the universe's grand evolution. And that, in itself, is a humbling thought. The idea of a black hole bouncing back from the brink of collapse sounds like pure science fiction until you dive into the math. Some of the most cutting-edge theories in quantum gravity suggest that under extreme conditions, a black hole's crushing collapse might not be the end of the story. Instead, like a cosmic rubber ball, it could hit a point of maximum compression and rebound, exploding outward in a burst of energy and matter. This isn't just wild speculation. It's a serious proposal emerging from loop quantum gravity, a framework that reimagines spacetime as a network of interconnected loops. According to these models, when matter reaches the densities predicted near a singularity, quantum effects could generate a repulsive force powerful enough to reverse the collapse, turning the black hole inside out. Picture this: a star collapses, forming a black hole as usual, but instead of crushing down infinitely, the core reaches a Planck-scale density, a trillion times denser than an atomic nucleus where quantum gravity takes over. At this point, the equations flip. The inward rush of matter transforms into an outward surge, like a spring recoiling after being compressed. What emerges isn't the original star, but a reshaped remnant, perhaps even a new universe budding off from our own. Some theorists call this a quantum bounce, and it could explain why certain black holes appear to flicker or stabilize rather than vanish into singularities. The evidence, while indirect, is tantalizing. Astrophysicists have observed brief, intense flashes of radiation from deep space events that don't fit the usual profiles of supernova or gamma-ray bursts. Could these be the echoes of black holes rebounding? One candidate, a mysterious transient event labeled GW190829, emitted a gravitational wave signal followed by an unusual X-ray flare. While conventional explanations point to neutron star mergers, a handful of researchers argue the data could also align with a rebound scenario, where a collapsing black hole's energy is momentarily trapped before erupting back out. Yet the theory faces steep hurdles. For one, the Planck scale is so far beyond our experimental reach that testing these ideas directly is currently impossible. Critics also note that a bouncing black hole would likely violate energy conservation laws unless exotic new physics is at play. And then there's the problem of entropy. If information isn't lost in a black hole but instead regurgitated in a rebound, how does it stay coherent? The universe isn't known for tidally reassembling scrambled eggs. Despite the challenges, the rebound hypothesis refuses to fade. It's part of a broader shift in how we view black holes, not as cosmic dead ends, but as dynamic transformers of matter and energy. Future gravitational wave detectors, like the proposed Einstein telescope, might catch subtle signatures of these quantum bounces in the reverberations of colliding black holes. Until then, the idea lingers at the edge of theory and observation, a reminder that even the universe's darkest corners might still hold surprises and second chances. Entropy isn't just about messy rooms or shuffled decks of cards. It's one of the universe's most fundamental forces, a relentless driver of chaos that governs everything from steam engines to supernovas. And when it comes to black holes, entropy might be the hidden hand keeping them from total collapse. Picture a black hole not as a static pit of darkness, but as a seething, dynamic system where disorder reaches a fever pitch just before the point of no return. According to the laws of thermodynamics, every system tends toward maximum entropy, a state where energy is so evenly distributed that no further work can be extracted. For black holes, this cosmic balancing act could create a tipping point where gravity's inward crush meets an equal and opposite push from entropy's demand for disorder, freezing the collapse in place like a paused avalanche. The math behind this idea traces back to Jacob Bekenstein and Stephen Hawking's groundbreaking work in the 1970s. They showed that black holes aren't just gravitational monsters. They're also thermodynamic objects with temperature and entropy. The larger the black hole, the greater its entropy, which scales with the area of its event horizon rather than its volume. This peculiar feature suggests that a black hole's disorder is encoded on its surface, like information scribbled onto a cosmic scratchpad. As matter falls inward, entropy skyrockets, potentially reaching a threshold where further collapse would paradoxically decrease disorder. Nature abhors such reversals, so the black hole might stabilize, its entropy acting like a speed bump to halt gravity's victory march. Consider the analogy of a collapsing star. As it implodes, particles are packed tighter and tighter, their possible configurations multiplying wildly, a hallmark of increasing entropy. But at some critical density, quantum effects or exotic states of matter could dominate, capping the chaos. It's like trying to cram more books onto an already overflowing shelf. Eventually, the system resists further compression, not because of lack of space, but because the disorder can't grow any further. For black holes, this entropy ceiling might manifest as a phase transition, where the crushing core transforms into something akin to a super-dense fluid, its particles arranged in a way that exhausts all possible disorder. This thermodynamic perspective flips the script on traditional collapse models. Instead of a one-way trip to a singularity, black holes might evolve toward equilibrium states where entropy, gravity, and quantum forces reach a standoff. Observations of certain supermassive black holes support this idea. Their measured growth rates often stall despite abundant surrounding matter, as if hitting an invisible entropy barrier. Even more intriguing are the black holes with flickering event horizons. Their turbulent surfaces could be thermodynamic engines in action, dissipating energy to maintain maximum entropy like a pot of water kept at a rolling boil. Yet mysteries linger. If entropy stabilizes black holes, why don't all of them exhibit this behavior? Some theorists argue that environmental factors, like the spin or magnetic fields of a black hole, might tip the scales, allowing certain ones to bypass entropy's limits. Others propose that the holographic principle, the idea that a black hole's interior is encoded on its surface, could redefine how we calculate entropy altogether, revealing stabilization mechanisms we've yet to imagine. The debate is far from settled, but each anomaly, every black hole that lingers when it should collapse, adds another piece to the puzzle. What's exhilarating is that this isn't just theoretical musing. Future gravitational wave detectors could spot the thermodynamic fingerprints of entropy-driven stability in the ripples of colliding black holes. Certain resonance patterns or energy distributions in these signals might betray the presence of entropy's invisible hand at work. Until then, the idea stands as a testament to how deeply interconnected the universe truly is, where even the coldest, darkest voids obey the same laws of disorder that govern our everyday world. And that's a thought both humbling and thrilling. Computer simulations have become the universe's digital laboratories, allowing us to test the laws of physics in ways reality won't yet permit. But sometimes these virtual experiments throw back answers we never anticipated, like black holes that refuse to collapse on schedule. In meticulously crafted simulations, where every variable is controlled and every equation derived from known physics, these digital anomalies emerge like cosmic glitches in the matrix. Are they simply artifacts of imperfect code, or could they be pointing to gaps in our understanding, hidden forces or phenomena we haven't yet accounted for in the real universe? Take the groundbreaking work of teams using tools like the Einstein Toolkit or the Chimera Code. These simulations recreate black hole formation with staggering precision, modeling the collapse of massive stars down to the millisecond. Yet in certain runs, especially those incorporating extreme magnetic fields or turbulent accretion disks, the black holes stall. Their event horizons flicker, their growth plateaus, or most perplexingly, their singularities fail to form entirely. It's as if the simulation itself is pushing back against the inevitability of collapse, hinting that our mathematical frameworks might be missing a crucial piece of the puzzle. One particularly telling example comes from a 2021 study at the University of Warsaw. Researchers simulating binary black hole mergers noticed something odd when they cranked up the resolution to account for quantum scale effects near the event horizons. Some merged remnants exhibited delayed collapse, lingering in a quasi-stable state for far longer than relativity predicts. The team initially blamed numerical artifacts, but after months of cross-checking, the anomaly persisted. Could this be a digital echo of real-world quantum gravity effects, something we've yet to observe directly? The stakes are higher than mere curiosity. If simulations consistently produce black holes that deviate from classical predictions, especially across different codes and initial conditions, it suggests our theories might need revising. Some physicists argue these virtual anomalies align with speculative ideas like Planck stars, quantum-corrected black holes, or gravastars, exotic objects with dark energy cores. Others caution that simulations, no matter how advanced, are only as good as their underlying assumptions. Missing physics like undiscovered particle interactions or higher dimensional effects could be the real culprits behind these digital rebellions. What's thrilling is that we're now entering an era where simulations and observations can directly converse. Gravitational wave detectors like LIGO provide real-world data to test against these virtual anomalies. A recent comparison found that certain merger echoes in LIGO data loosely match the waveforms predicted by simulations with stubborn black holes. The match isn't perfect, but it's tantalizing enough to spur more research. Future projects like the Square Kilometre Array or the next-gen LISA Gravitational Wave Observatory could finally bridge the gap, revealing whether these simulation quirks are programming oddities or glimpses of physics waiting to be discovered. Perhaps the most provocative possibility is that simulations aren't just mimicking reality, they're ahead of it. By freely exploring parameter spaces beyond what's observed, like ultra-high spin rates or exotic matter compositions, they might uncover behaviors real black holes could exhibit under untested conditions. It's akin to how fluid dynamic simulations predicted rogue waves decades before oceanographers confirmed their existence. The universe, after all, has had billions of years to experiment with extremes we've barely begun to imagine. For now, every anomalous simulation serves as both a challenge and a compass. They force us to question whether our equations are complete and guide us toward the observations that might settle the debate. In the grand quest to understand black holes, these digital universes aren't just tools, they're collaborators, whispering hints about where nature might be hiding its next great revelation. The next decade promises to revolutionize our understanding of black holes in ways we can barely imagine, thanks to a new generation of telescopes and detectors designed to probe the universe's deepest mysteries. At the forefront is the Laser Interferometer Space Antenna, or LISA, a gravitational wave observatory set to launch in the 2030s. Unlike ground-based detectors like LIGO, which catch the final seconds of black hole collisions, LISA will operate in space with laser arms spanning millions of kilometers, sensitive enough to detect mergers weeks or even months before they happen. This unprecedented window into black hole dynamics could reveal whether collapse anomalies like those distorted remnants or flickering event horizons are cosmic flukes or fundamental features of how black holes evolve. Imagine catching the moment two black holes spiral toward collision, only to leave behind a wobbling, half-formed remnant instead of a smooth singularity. LISA precision might finally tell us if these irregularities stem from quantum effects, hidden dimensions, or something even stranger. Meanwhile, the James Webb Space Telescope is already peeling back layers of the cosmos with its infrared eyes, uncovering black holes in regions where they shouldn't exist. Recent observations of unexpectedly ancient supermassive black holes, some dating back to within just a few 100 million years of the Big Bang, have thrown conventional formation theories into chaos. How did these behemoths grow so large so quickly? Could primordial black holes or exotic collapse mechanisms have seeded their rapid growth? Webb's ability to peer through cosmic dust and detect the faint glow of early galaxies might hold the answers. By mapping the environments around young black holes, we could uncover clues about whether dark matter halos, magnetic fields, or other unseen forces played a role in stabilizing them during the universe's infancy. But the revolution doesn't stop there. The Vera Rubin Observatory, with its panoramic view of the sky, will scan for transient events, sudden flashes or distortions that might signal black holes behaving oddly. Picture a supermassive black hole momentarily hiccuping as its event horizon resists collapse, or a rogue intermediate black hole drifting through our galaxy, its presence betrayed by the way it bends starlight. Rubin's relentless gaze could catalog thousands of these anomalies, turning statistical noise into concrete patterns. Similarly, the Einstein telescope, a next-generation gravitational wave detector, aims to listen for the faintest whispers of quantum fluctuations near event horizons. Its subterranean design will filter out Earth's noise, potentially capturing echoes or reverberations that reveal whether black holes truly have holographic surfaces or hidden quantum structures. The most tantalizing possibilities lie in the synergy between these instruments. Imagine Webb spotting a peculiar black hole in a distant galaxy, while LISA simultaneously detects gravitational waves from its erratic movements. Cross-referencing these datasets could unveil whether magnetic fields, spin rates, or accretion disk turbulence are the hidden architects behind collapse resistance. Or consider the potential for citizen science. Projects like Black Hole Hunter already enlist the public to scour telescope data for gravitational lenses, subtle distortions that might reveal hidden black holes. With millions of eyes and algorithms combing the skies, we're entering an era where serendipitous discoveries could upend decades of theory overnight. Yet the greatest breakthrough might come from the unexpected. Every leap in observational capability has unveiled phenomena we didn't know to look for. Gravitational waves themselves were once deemed nearly impossible to detect. As these new tools come online, they might uncover black holes entangled in higher dimensional brains, or ones emitting strange new particles that hint at undiscovered physics. The anomalies we've puzzled over could be just the first threads of a far richer tapestry, waiting to be unraveled by the keen eyes and ears of the next generation of cosmic explorers. The future of black hole research isn't just about answering old questions, it's about discovering questions we haven't even thought to ask yet. Hollywood loves to paint black holes as cosmic vacuum cleaners, endlessly devouring everything in their path, planets, stars, even entire galaxies. But the reality is far more nuanced. While black holes do possess unimaginable gravitational pull, their influence isn't limitless. Take the myth that black holes suck matter in like some unstoppable force. In truth, matter must cross the event horizon to be lost forever, and outside that boundary, orbits can remain stable. Picture our own Milky Way. Billions of stars orbit Sagittarius, a star, the supermassive black hole at our galaxy's center, without being swallowed whole. Gravity behaves the same way around a black hole as it does around any massive object until you cross that fatal threshold. Another common misconception: that all black holes collapse into perfect, infinitely dense singularities. As we've seen throughout this video, nature loves exceptions. From quantum fuzz to magnetic scaffolding, numerous mechanisms might halt or alter collapse, leaving behind structures more complex than a simple point of infinite density. Even the event horizon, often depicted as a static, smooth boundary, can flicker, wobble, or stall under the right conditions. These aren't flaws in the science, they're reminders that the universe is messier and more inventive than our tidy equations often predict. Then there's the enduring myth that black holes are portals to other universes or time machines. While wormholes are mathematically possible in Einstein's relativity, they'd require exotic matter with negative energy to stay open, something we've never observed. As for time dilation, yes, time slows near a black hole's gravity, but the idea of hopping through one to visit the past is pure fantasy. The tidal forces would shred any matter into subatomic particles long before it could reach the interior. Perhaps the most persistent fiction is that black holes are rare, lurking only in distant galaxies. In reality, astronomers estimate there could be over 100 million stellar mass black holes in the Milky Way alone, remnants of massive stars that lived and died before our solar system even formed. Some might drift unseen just light years away, their presence betrayed only by subtle gravitational tugs on neighboring stars. Debunking these myths isn't just about setting the record straight, it's about appreciating how much richer black holes are than their pop culture caricatures. They're not just destroyers, they're cosmic engines shaping galaxies through their jets and gravitational influence. They're not just endpoints, they're laboratories for the most extreme physics in the universe. And they're certainly not solved puzzles. Every anomaly we've explored hints at deeper layers waiting to be uncovered. As we move toward our final reflections, remember, the truth about black holes isn't found in the myths we've outgrown, but in the mysteries that still defy explanation. If black holes can defy total collapse, the implications ripple across billions of years, reshaping our vision of the universe's ultimate fate. Conventional cosmology paints a bleak picture, a cold, dark end where black holes slowly evaporate via Hawking radiation, leaving behind nothing but a fading whisper of particles. But what if some black holes persist, their structures stabilized by quantum effects, dark matter, or forces we've yet to discover? This possibility cracks open the door to a radically different cosmic finale, one where these gravitational titans outlive even the dimmest stars, becoming the last structures in an otherwise empty universe. Consider the far future, trillions of years from now, when galaxies have dispersed and star formation has ceased. In this era, known as the Degenerate Age, the only sources of light might be the faint glow of white dwarfs cooling into black dwarfs, a process so slow it's never occurred in our 13.8 billion-year-old cosmos. Yet amid this darkness, persistent black holes could remain active, their event horizons flickering like dying embers. Some theories suggest these long-lived anomalies might even become anchors for hypothetical civilizations of the distant future, harnessing their energy as the last usable power sources in a heat-dead universe. Far from being mere relics, they could transform into cosmic lighthouses, their gravitational influence structuring whatever sparse matter remains. But the ramifications go deeper than longevity. If black holes resist collapse, their accumulated mass might alter the universe's expansion. Dark energy, the mysterious force accelerating cosmic growth, could face an unexpected counterbalance. Imagine a scenario where stabilized black holes act as gravitational knots, subtly slowing the dispersal of matter on cosmological scales. Over eons, this might delay or even prevent the Big Rip, a hypothetical endgame where dark energy tears apart galaxies, stars, and eventually space-time itself. It's a delicate dance, one where the universe's fate hinges on the interplay between black holes' gravitational pull and dark energy's relentless push. Philosophically, these possibilities force us to confront profound questions about cosmic order. Why would nature allow exceptions to black hole collapse unless they served some deeper purpose? Could these anomalies be clues to a hidden symmetry, a universe that self-regulates to prevent total entropy? Some theorists speculate that black holes might be cosmic recyclers, their stabilized interiors birthing new universes in a cycle of creation and destruction we're only beginning to glimpse. This idea, rooted in the mathematics of bouncing cosmologies, suggests that what we perceive as a black hole's interior might be the seed of another spacetime entirely, a fractal reality where every collapse births a new beginning. Yet skepticism remains. Critics argue that even if some black holes avoid total collapse, their numbers would be too small to meaningfully influence the universe's trajectory. Others contend that Hawking radiation ensures all black holes will eventually decay, regardless of quantum delays or exotic matter. But the mere possibility of exceptions challenges us to rethink cosmology's assumptions. Every anomaly, every black hole that lingers where none should whispers that our models are incomplete, that the universe's endgame might be stranger and more nuanced than we've dared to imagine. The most thrilling prospect: we might not need to wait eons to test these ideas. Advanced simulations and next-generation telescopes could soon reveal whether black holes exhibit behaviors that tilt the cosmic scales. Observations of ancient quasars or gravitational wave echoes might hint at stabilization mechanisms already at work. As we peer deeper into the abyss, we're not just studying black holes, we're reading the universe's last will and testament, deciphering clues about how this grand story ends. And if the cosmos has taught us anything, it's that the final chapter is always more surprising than we expect. From stubborn supermassive black holes to quantum fuzz, the mysteries we've explored today reveal a universe far stranger than textbooks suggest. These cosmic rebels, black holes that refuse to collapse as expected, aren't just scientific curiosities. They're windows into the gaps in our understanding, places where gravity, quantum mechanics, and the fabric of space-time itself collide in ways we're only beginning to grasp. Every anomaly, from M87's eerily stable giant to the flickering event horizons that seem to pulse with hidden energy, forces us to ask, what rules is the universe truly playing by? Think of these black holes as cosmic detectives, each one holding clues to questions we haven't even fully formulated yet. The way intermediate mass black holes linger in cosmic purgatory, neither collapsing nor growing, might hint at undiscovered forces acting on scales we've never probed. Those gravitational wave echoes, repeating like faint cosmic whispers, could be the first murmurs of quantum gravity making itself known. Even the most speculative ideas, like black holes wrapped in dark matter halos or bristling with quantum hair, aren't just imaginative exercises. They're necessary leaps to explain what our current theories can't. What's thrilling is how rapidly this field is evolving. A decade ago, we'd never directly seen a black hole's shadow or detected gravitational waves. Now, with tools like the James Webb Space Telescope and next-generation detectors on the horizon, we're poised to peel back even more layers of these enigmas. Imagine future observations catching a black hole mid-rebound, or telescopes spotting the subtle imprint of higher dimensions in a merger's afterglow. The discoveries ahead could rewrite physics itself, but here's the most humbling truth: for all we've learned, the universe keeps reminding us how much we don't know. Those black holes that stubbornly resist collapse, they're not glitches in the cosmic code, they're proof that reality is richer, messier, and more inventive than our models can capture. And that's what makes science so exhilarating. Every mystery solved unveils new questions. Every anomaly explored opens doors we didn't know existed. If this journey through the cosmos's most head-scratching puzzles has sparked your curiosity, you're not alone. The greatest discoveries often start with someone staring at the night sky and wondering, wait, that shouldn't happen. So whether you're an armchair astronomer or a seasoned space enthusiast, keep asking those questions. The universe has plenty of surprises left, and who knows? The next big breakthrough might come from an idea born right here, in the comments or conversations this video inspires. Thanks for joining me on this dive into the unknown. Don't forget to hit like, subscribe, and let me know which cosmic mystery fascinates you most. Until our next adventure among the stars, stay curious. The cosmos is counting